start looking at the in-depth of those processes, we would know what does a specific term process mean. So GTR, he'll be posting his office hours soon. So I'll maybe send a message through Blackboard to let you know, but you can always email him or ask him an appointment, and he'll be able to help you with homeworks, with any questions that you have. And of course, he'll be taking care of you guys in the lab itself. So we looked at lithography. Let's look at oxidation. Most of the lithography steps that we do, we always have some hard layer first made up. Mostly that layer is oxide, and then we apply photoresist on top of that. Photoresist is what we use to transfer the pattern from mask, and then we use that photoresist as a soft protection layer to transfer that design, that feature, into that hard layer which is beneath it, which is mostly oxide. How do we transfer that design into the lower layer? You can etch it, or you can diffusion. Of course, to do diffusion, we'll have to open that hard. We'll have to do etching first, but we can do something else. Etching is removal of material. We may want to deposit material at certain places only, right? But then I'd say, okay, if I deposit something, it's going to cover everything. It's going to cover that trench that I made, but it's going to cover photos at other places as well, right? So we have some ways of removing photoresist and the material that we deposit on top of photoresist away. So what we are left with is just that feature which would have that extra material deposited on top. But mostly we do etching. And what do we use to etch oxide? Again, BHF, right? Buffered oxide etch or BHF. And what's the etch rate of 6 to 1 BHF?
Speculation.
What are you speculating? How much is the etch rate? No. What is the etch rate? How fast does BHF etch silicon dioxide? As a rule of thumb, 1,000 angstroms per minute. But you always characterize that. So, as a general rule, 1,000 angstroms per minute, 100 nanometers per minute. So, before you start your etch of oxide, you have to know how thick your oxide is, because then that will define how long should you keep the chip dipped into the BHF. Right? Make sense? Once we get to etch, we'll see we always over etch. We always do 20% extra time to get rid of everything. But oxidation is something which is used for most of the steps. What is oxidation?
Growing oxide and solvent.
Growing oxide, of course, yes. What is oxidation? Just oxidation. It is a reaction between oxygen and the material. In this case, it's the oxygen and silicon, right? For every 100 units of oxide grown, how much of silicon gets consumed? 44 units, right? So if it's 100 micron of silicon dioxide that we grow, we would have consumed how much of silicon? 44 micron, right? If we grow 100 nanometer of oxide, how much silicon we would have consumed? 44 nanometer, right?
So you end up with 66 nanometers of oxide?
So we end up with a surface which is 66 units higher than the original starting surface of silicon, right? 56, yeah, 45. So in this course we'll use 44, but you'll see the number is 42 somewhere there, say 46. Depends on the orientation of silicon and many other factors. But we take 44 as a standard number in this course. So even if we don't do any special processing like high temperature or humid environment, silicon always forms an oxide layer, which is called native oxide. What do you think? Native oxide is good or bad? Yeah. Native oxide is good or bad?
Depends on what you're doing.
Depends on what you're doing. If I leave my wafers for a longer period of time, can I live with native oxide? Okay, remember many times this oxide or nitride layer, we use them as the final material that covers everything, and we call it passivation layer. Right? It buries everything, so everything buried below. There's no more chemical change that can occur because now we have this protection layer on top. So native oxide is good in a sense. It reduces the oxidation rate. Now we have a small layer, so and we discussed that oxygen species have to seep through or diffuse through that oxide layer and get to the interface to continue oxidation. So having native oxide is good in a sense. It doesn't let further oxidation occur. It protects the silicon surface, right? So if I leave it for longer period, I want some oxide to be there, so the silicon that's beneath doesn't get contaminated. And contamination is again those three things, which can be particles, which can be films, and which can be ions, metallic ions that can change the electrical behavior of silicon, semiconductor. So we many times want it. Of course, we want to get rid of it before we do oxidation, right? How do we get rid of it? The HF only, right? Dip it in. We have about half an hour before this really forms up again. Or we may not want to do that. If the oxide thickness is measurable, I can still start with that wafer and continue and do oxidation on top of that. Right? I can, right? Or not?
If you want to do oxidation on the wafer, it's allowed.
If I already have an oxide and I can measure it,
And I want to do oxidation to the wafer, then it's okay. If I want to do some other process,
right?
Then
Exactly. So it depends on process. If I want to leave that native oxide, because if I'm depositing something, those metals, maybe chrome, may not stick to oxide at all. It would stick to silicon very well. In that case, I might want to get rid of it. But just if I have to oxidize the wafer further, I can leave native oxide there and continue oxidation on top of that. Now, my estimate will be now adjusted for that initial oxide thickness, right? So we'll see the relation, how do we calculate. So we'll have to figure out how to incorporate that oxide which is already there before we start oxidation. So, of course, a good insulator has good quality and we can control the thickness precisely. It has different properties than silicon. And say properties, electrical properties, physical properties, chemical properties, all sorts of. So just by reaction with oxygen, it results into a material which is very different than silicon. How do we do it? This is just a picture, and probably won't be clear to you unless you see the system. But essentially, this is loading area, but this is where there is furnace, probably 8 feet behind it. This is a smaller furnace, so this is the opening of that furnace. Is nothing but a glass tube which has a small opening, and it grows, and then it's continuous cylinder, and it's closed from behind. We have opening for gases. In that outlet, we have this opening for where you load the wafers. And how do we load the wafers? We have these boat type of glass thing, which has notches on the glass thing. Let's say quartz, we call it boat. Quartz boat, and we put the wafers lying with each other. There are notches here, so we match the notch, and there are notches at the bottom. So we put the wafer upright into that boat, and we put them in line, and then we push the boat with a again glass rod type thing, which has this kind of hook, and here we push this into the tube. In this case, it's a bigger tube, so this is that boat that I was talking about. It has wafers on it. We push it to go all the way in. Once it goes in, we control the gases and we control the temperature. And what happens is the reaction starts only in silicon dioxide to grow silicon dioxide. Again, it's wet or dry. Wet is where we don't have any vapors. Wet is where we have vapors, and dry is where we don't have any water vapor. So, what do you think? If you have water vapor, should the oxidation be faster or slower?
Faster.
Faster? How do you presume that?
Slow.
Pardon? Should it be faster or slower? Slower? Vapor, water vapor. Those who have lived close to coastline, they know that
I know.
metal
Water is very
oxidizes
corrosive generally.
very fast. Right? If you live close to coast, metal oxidizes very fast. Things go bad very quickly. So, with water content, it's fast. Without water content, it's slow. So, dry oxide. Just remember these two things. There are two types of oxide: dry oxide, wet oxide. Dry oxide is slow to grow, high in quality. Wet oxide is fast to grow, low in quality. And by low or high in quality, we'll see what are the parameters that matter for quality. But generally, there are two ways how do we grow them. One is called, and always remember when I'm saying grow them, oxidation is when we consume silicon to put a silicon dioxide film. But if I'm depositing silicon dioxide, that's a totally different process, right? So we can deposit silicon dioxide, which wouldn't consume any silicon, but that will not be called oxidation. Oxidation is only this process where we use silicon to grow silicon dioxide.
And when we deposit, is that do we vaporize or are we precipitating silicon?
We'll see. It's a chemical process. There's a reaction that occurs between between gases, and those byproducts is silicon dioxide, which gets deposited on the surface of the liquid. So, how to use it? We use it as etch mask, which as gave you example at the start. We want to have a layer of oxide, and then we do lithography and then transfer the pattern. We etch the pattern in there. So we can then do further etching of silicon and use silicon dioxide as an etch mask. Make sense? So I can, in that case, for lithography, we do first step where we have this was photoresist and this is silicon, right? So I use photoresist to transfer this pattern in silicon dioxide. I do my BHF and I transfer that pattern in silicon dioxide, right? And I can do further processing, but before I do further, I'll get rid of that because I don't need that. And I'm getting rid of that because the resist can come off and become lodged, those particles somewhere, and lose the etching condition, change the etching condition here. I can do etching in silicon using this guy as a mask or whatever recipe I use, whatever chemical I use for silicon etching, right? That's called etch mask, right? If I use something like this, we call it hard mask, which means a layer of a material which is hard, which is very, what's it called, in very intimate contact with the material, which is grown on top of that material and just adhering very well to the surface. Use that as a hard mask.
What's the optical window? Is silicon dioxide transparent?
Yeah.
Is that-
Yeah. Next Wednesday you should be able to see that. So I forget, I should bring some wafers.
It's the other type of mask. It's called hard mask.
Yeah, so other is just call it lithography mask, which would be photoresist. Now, while at it, and it's gonna come soon. When I was at this step, and I just have silicon dioxide, and I have this opening of photoresist, and we use BHF to etch silicon dioxide, right? So we say, okay, BHF etches silicon dioxide as 1,000 angstroms per minute. What can we say about its interaction with photoresist? What is the ideal requirement for the reaction of BHF with photoresist? It shouldn't, right? So we call this property selectivity, as selectivity of etch. So when we talk about it, we would say BHF is very selective between silicon dioxide and photoresist. And there are always numbers which are given. It can be 1 to 6 selectivity, 1 to 100 selectivity, which would mean that if it etches 6 times silicon dioxide, it's going to etch only 1 time of photoresist. Ideally, there should not be any reaction. There should be no reaction, but there is always some reaction. So again, ideally, that reaction should be way slower than the reaction between the material that we really want to remove, right? So this is the word selectivity. For any etch, we are always worried about selectivity of the recipe. When I say recipe means, okay, you have BHF, you have first HF, which is diluted to some concentration, and then you have to use it in certain containers, right? Because BHF etches silicon dioxide, and silicon dioxide is nothing but, what is silicon dioxide? Glass, right? So we cannot use glassware to hold BHF, right? Because it etches BHF. It etches glass, it etches silicon dioxide. So we have to use containers made of what? Plastic? Teflon. Special type of polymer. Special kind of plastic.
Teflon doesn't really get affected by BHF?
So we use Teflon tweezers or Teflon coated tweezers. We use Teflon containers. We use Teflon wafer holders, like the one which we can use to dip it, right? So that's all part of recipe. So you would know, okay, I have to etch silicon dioxide. Now the whole 9 yards, you should know whatever is the requirement. Very often what we do is the BHF comes in a bottle which is made of Teflon. So once you're done with it, you cut the bottle and use the lower half. That's your recap for BHF. Right? But you have to keep it clean again. So we use it as etch mask, we use it as optical window to look what's below because it's transparent. We use it to cover the field everywhere so devices don't interfere with each other. And one can say that field means a level playing area. If you cover that, fine, but the devices are embedded between the substrate, right? So those doping has happened in z-axis. So what is the big deal if you cover the top, right? So it's not just the plane that we cover, we make trenches between devices and we cover those trenches with silicon dioxide, right? So the special way, what we call shallow trench isolation, we'll look at that as well.
I'm kind of confused. If silicon dioxide is transparent, then why do we use a color chart to measure oxide?
Yeah, it's transparent, but it has a color. It's using sunglasses. They're transparent. You can see through, but you see through a color. Yeah. So it's a film which is glossy, but it changes color as the thickness changes.
Bright reflections?
Pardon?
Is it bragg reflections?
We'll see where the colors come from. That's part of metrology. It's not Bragg's reflection. I think it's internal refraction, and they cancel out some wavelength, something like that. So, and of course, we use it as gate oxide. How do we measure, or what models govern the oxide growth? It's called Dale and Grove's model, which was the paper that I asked you to read. Should be familiar with that theory. What it defines is it gives us a time that we would need to grow an oxide thickness. Given we know the temperature that we are using and we know the rate constants. So it can go both ways. If I know the time that I want to use, I can figure out what's the thickness I will get. Right? But that's not good for thin oxide. That's a different model. Once we get into oxidation, precisely we'll see what happens there. So if you look at this guy, so this is the thickness of oxide, which is just a few monolayers in oxide, making them that thin layer at exactly the same uniform thickness all over the 16-inch wafer has been a challenge. So that is what has been replaced now with other materials, what we call high K dielectric materials. And we still measure their thickness in terms of oxide thickness, in terms of equivalent oxide thickness. So we'll see what does it mean by EOT, equivalent oxide thickness. So the idea is that if you use high K dielectric, we can use a physically thicker layer of insulator and get same capacitive effect what we get from oxide. Right? So since the whole technology is the physics of devices is based on oxide thickness and behavior of that insulator, we convert this other materials into EOD, equivalent oxide thickness, and use that in measuring the behavior. And that is one of the features which defines the node also, what node we are. But generally it's the half pitch, or how often can you repeat two, what do you call, lines interconnect, right? But it can be any smallest feature that we can make. That is what is defined as the node, 65 nanometer or 45 nanometer or 22 nanometer. It can be the gate length also. So ITRS defines the node based on what is the smallest feature size in a given technology that is being made. Right? So in 65 nanometer, the length of channel is 35 nanometer, oxide thickness is 1.2 nanometer, and drain voltage is 1.2 volts. So again, this device, we probably don't have to go through the physics of this device, but the basic structure is something we have to be familiar with. Right? So there is a source region, a drain region, a gate, and these regions are heavily doped with a type which is different than the substrate. So P-type substrate, we have N-type device in there. That's the idea of complementary MOS, CMOS. Anyway, oxidation or oxide thickness is one of the critical factors in the whole device technology. We looked at the theory that semiconductors are neither insulators nor conductors, but to make them electrically responsive, we incorporate external impurities. We incorporate certain impurities, which may belong to group 3 or group 5. Right? And what they do is either accept an electron or donate an electron. In either case, we say either it's the N-type or it's a P-type. Either we have majority of electrons or majority of holes. When you say majority of one type of carrier, does it mean there is no other types of carriers in that material? When we have majority of one party in house, it doesn't mean there's no person of the other party. The other party is still there, but they are minorities, right? So we have once we call intrinsic semiconductor, we have how much of holes and electrons do we have in intrinsic semiconductor? Should be equal. How much is there? 10 raised to power? 10 raised to power 10. So we in intrinsic semiconductor we assume it to be some number times 10 raised to power 10 of holes and electrons. But we kick the number one type of those things up by introducing external species from groups 3 or 5. How do we incorporate those? So a simple concept is diffusion, right? And how do we define diffusion? How do we
Something moving from high concentration to low
to
concentration.
low concentration? Something moving under no external field, right? If it's external field, then there is a drift concept, drift component to it. So it has to move on its own, right? But that's good for if the medium is the same. If you have gas medium, I open maybe a perfume here and the molecules travel to the other side. It works if I throw a drop of ink in water, so the ink diffuses. But what if I have high concentration in gas state and I want it to diffuse in solid surface? Have we ever seen that kind of diffusion? Do we
Happens.
see diffusion occurring across mediums?
Sure.
Where?
Well, you put something in your freezer, and your ice creams are probably going to start smelling out like your freezer.
So what is happening in freezer?
The molecules of the things that you don't want.
It's a temperature which is way different than normal temperature, right? But say it again. So what happens in freezer? We put them. So that's evaporation. That's the thing, right?
No. If you, let's say you got something that doesn't necessarily smell good in the freezer, you put an ice cube there. Ice is solid, but you know that it's going to happen very slowly. But what you don't like is those other molecules are probably still going to diffuse into your ice cube very slowly. I mean, hotter would be better, right?
The hotter. So we don't see this intermediate diffusion at room temperature, right? But what if we give enough energy to those molecules or atoms? They can do that. They can cross the barrier and start diffusing just under the potential of the concentration gradient, right? So concentration gradient is what we know, but it's the potential that is caused by that potential, which makes some work to occur, right? So we do that in semiconductor devices. So we put them in a furnace again and raise the temperature really high, and we introduce those gases which you want to diffuse into silica. That's one way how we do doping. And the other one is by force, where we can inject them. That's called implantation. So, but the basic idea is that we do this to introduce specific impurities to change the electrical behavior of semiconductor materials. And we do that for N-type and P-type to have specific devices made out of it, diodes, transistors, right? We can also do that to create an embedded layer of a material which is different than the substrate. The simple example is if I want to make a silicon dioxide layer, I can do that on the top and bottom by oxidation. But if I want to make it in the middle of the bulk, I can do that as well. Not by diffusion, because if I do diffusion, I cannot control the concentration of oxide in a confined region. This will clear up as we go along. Simple thing to understand is if I define depth in this direction, depth into substrate. So if I have my wafer like this silicon and maybe silicon dioxide on both sides, and I'm just taking this interface of silicon. So, and this is concentration. If I do diffusion, this would look like something like this, right? There will be higher concentration, and if I continue the process, these atoms or molecules will keep on traveling further within the surface, right? And they'll keep on going given I have continuous unlimited supply of those atoms there, right? And ultimately what I get now, if I flip this upside down, what I'm getting is I have much more concentration of, and it goes down as I move away from the top surface, right? That's diffusion. The other way is implantation, where I bombard some ion, and instead of having this high concentration of the surface, I have their concentration somewhere in the middle, where you might have some high concentration. Implantation. It's like firing those ions on a surface and letting them penetrate through the surface. Now, if I want to achieve X number of doping, what can I do with the number of ions that I bombard on the surface? If I want to have high number of dopants, for example, I can fire many more of those ions. What we call dose. Right? Dose is the same thing, that how many of them are falling on the surface. Another way is I can keep on shooting them for longer time. So it's dose and how long do we do that dose. So both of these things define intensity of the ion bombardment. So these are two concepts that we use for for doping. First is diffusion. In diffusion, we can use silicon dioxide as a hard mask, and we can have a cocktail of recipes, cocktail of gases according to our recipe, and do it at high temperature. During the process, those ions will incorporate into the bulk. And in this case, what we get is phosphorus incorporated, which is an anti-material, right? So, yeah, oxidized wafer, open the window where we want this to happen. We remove photoresist. We remove silicon dioxide also before we remove photoresist, and we introduce the dopants. It's heated to a really high temperature, and thermal energy makes them travel. Now, this is a high temperature process. I did diffusion, and whatever depth I expected, I got that. Now I do a bunch of other process, maybe 6 process down the road. I have to do a high temperature process where I have to take it to 1000 degrees centigrade. What do you think will happen to this concentration of P-type dopants?
Probably spread out
It's
further.
going to spread out further, right? So if I do another 1000 process, they can spread out even further. Will I have my N-type well left there? Will I have my source region? Does it make sense what I'm saying? So we do doping, and we know, okay, this is the region where I have X number. So 10 raised to 10 was the background concentration. So I doped it to 10 raised to 18. But now I did another thermal processes. I might have come back to maybe 10 raised to 10. The electrical properties of that area would be completely changed. So that is what is called back end of line process and front end of line process. So We can do many things once we start, but once we are having many of these diffusion layers, we don't have too much thermal room to play with. Or what we can do is we can calculate that diffusion, and we would know, okay, if I do another 1000-degree process for 10 minutes, this is going to diffuse in this way. So I can start with a certain number of dopant. So after those 3-4 steps, I would end up with what exactly I wanted there. Does that make sense? But only if I have something below this substrate to make sure this doesn't go all the way and beats the other devices. Laterally or horizontally. Vertically and horizontally. We'll get to that. For now, it's just the basic idea of diffusion. Or we can do implantation. And implantation is, so in diffusion, they gradually diffuse because of density. And the final concentration is non-linear. It's something where you have high level, and then it falls down and gets to the background concentrations. And once we bring it down, the dopants, they become fixed in their positions. And have you guys ever heard of first law of diffusion? Okay. Those who have never come across fixed first law of diffusion. Those who have not come across. Yes, ma'am. If you don't know, you need to tell me so I know I have to, what level I have to do.
I heard it, but I don't remember what it is.
Okay, what essentially it defines is, it defines the J, which is the flux. How much of something would be passing in a cross-section in unit area in response to the difference in concentration. Right? So partial C or partial X, where C is dependent on X and T, time and distance, but it's changed with respect to distance. So essentially the same thing, that I go deep. When you go deep, my movement of my impurities, movement, right, flux, will change because the concentration gradient is not a whole lot different. Especially once you get here, this is not too much difference. So they're going to be very, very, very stable there. So it's the rate of the solute per unit area with respect to the concentration of the solute in X. In D is constant. We take D as constant at a given temperature. So if I have unlimited supply of dopants, I end up with respect to time, I end up with a profile something like this. So if this is the top of the wafer, and if I look at concentration, I'll have high concentration, it will fall down, right? If I keep on supplying unlimited source, this is gonna diffuse further. But if I have limited supply, whatever I incorporate at start is gonna become diffused over more distance from the surface. So it makes sense? These two cases are very important. If I have a diffusion where I want to restrain the dopants, but I want them to go deep, there's a different recipe. But if I want to have a gradual change and I want to have as much dopant as I want, there's a different recipe for that. And second law of diffusion now defines it in respect to the concentration itself, with respect to the distance within the substrate. We'll look at these guys more closely once we get there. So this is that idea that we start with certain depth, but with time this would increase to take more depth. Now this is not, that's okay, so this is 10 to the 21, 10 to the 19, 10 to the 16, and then essentially when it drops off, it goes to the background concentration, which is 10 raised by 10. So again, these are two cases of limited and unlimited supply. So this is unlimited, this is limited. And more recently, what we do is we do in rapid thermal anneal. We do it very quick process, but then we supply very high concentration of dopants in those kind of processes, right? So once we do the doping and they all get to their locations, they are not electrically active. So we have to do a thermal process where we activate the dopants. Essentially what we do is we let them find their place in the lattice, where they have to replace a silicon atom and take the place of that atom. We'll look at those also, what are those positions called in the lattice where those dopants go. But once they get to that, once they become part of the lattice, only then they can contribute the carriers. Does it make sense? If they are not at exactly the edge of a lattice, they cannot contribute their carriers. So they have to be brought together, what we call activate the dopants. And that process also does what we call healing of the crystal. So diffusion is high temperature process, right? And what we get is a profile which is non-linear, but which has two types, where we have unlimited source or limited source, and that depends on how does the concentration change with respect to distance from surface. In ion implantation, essentially we are bombarding the wafer with ions, and we want them to reach certain depth and stay there. Right? If we are making source and drain, we just want them to stay close to the surface. Right? So again, two factors: what is my dose? How many of them am I bombarding? And at what energy? And for how long? Right? Does it make sense? So if I have this anti-aircraft bullet which is this long, or a small bullet, which one will penetrate further? Small one? Small one? So
One
they-
that they're moving at the same speed.
the ones which they want to, what do you call, penetrate concrete or thicker walls, they are supposed to be small. They are large because they carry more momentum once they get to the surface. Similar concept for ions. If we want them to go deeper, we have more energy supplying them, so they will get deeper into the substrate. If you want them to stay close to the surface, there's less energy retrieval. So ion implantation is essentially bombarding of ions from an ion gun onto surface. In this case, you see the words called lens, but using ions. So lens is nothing but these bunch of coils which focus or change the beam, right? They do the same process what an optical lens do, but here what we are playing is the beam of ions. And then we can raster that beam on the surface, right? You know what's raster? We can make it walk in one direction while it's moving in the other axis as well. So as they enter silicon, they collide and knock down silicon from their lattice position, and they come to rest depending on what was their energy. And what it gives us a statistical distribution at certain depths. And statistical distribution is some of them will come to rest earlier than what we wanted them to do, and some of them will move a little further than what we want them to do. But we'll have maxima at certain depths, right? So this is now I know how deep I wanted this to be. Make sense? So we are bombarding those ions, and they are traveling within most of them will come to rest at rested depths, but some will come to rest at before that also. But there will be lesser numbers. So we have this Gaussian distribution once they get inside. So again, we do a pattern. We have exact placement of token at exact depth, and because they have now damaged the lattice, they have damaged because they have kicked off silicon atom, they have to get heated up to activate. So we do, after both of the doping processes, we do heat process in the absence of those gases to do what? It's called annealing. So why do we do annealing? To damage, to heal the damage to silicon lattice and to activate the dopants. And activation means placing them in the exact place in the lattice, right? Just
The difference between diffusion and ion implantation is only the way they enter the silicon.
right.
Once they are incorporated in the silicon atom, is there a difference in the electrical properties of silicons?
No.
Then I have read that resistors which are ion implanted have a higher voltage rating than the ones which are
Yeah.
diffused.
So once they get into the substrate, one case does more damage than the other. In diffusion, we are not doing a collision between atoms, right? We are not doing collision between ions and atoms. In case of implantation, that's exactly what we are doing. So their electrical properties are slightly different, but it's not different in terms of the doping itself.
But then, why is the voltage rating higher for ion implanted?
We'll get there. We'll look at the difference in both cases, why one is preferred over the other. So that's one part why this is. So the simple reason is, in case of implantation, we can confine the majority cases in a very narrow distribution. We cannot do that in case of diffusion. So all the impurity that I'm incorporating is a very well confined depth in case of implantation, not in case of diffusion. So their contribution is different in both cases. But if you look at the structure, they're exactly the same. There's no difference. Once you heal them, they're the same.
So what do we implant to make a resistor? Because ions generally, increase conductivity. How do you decrease conductivity?
Ions decrease conductivity.
Increase, right? I mean, ions are charge carriers.
Okay. So when you have a conductor which is supposed to conduct one type of carrier, and you are looking at the other types of carriers, so it depends on the majority and minority.
I see.
So what is the current? Are you taking electrons as current or using volts? It depends on the type of device you are working with. So we'll get to that. Why? That's the idea of CMOS integration, where you have a resistor with one type of doping in it. What are the electrical properties that you are worried with? Right? So we do two steps, annealing, and so diffusion and implantation is always followed by annealing. It's a low temperature process, very well defined doping, but there's more damage, and the annealing is done at high temperature in this case. But we recover most of the damage. So the profile for this guy is Gaussian, so seal and groove model doesn't apply. Not the fixed diffusion model doesn't apply here. So if we keep on doping them higher and higher, what happens? Should we get a resistance with low resistivity? Resistivity will keep on increasing if we keep on doping it, right? You all agree on that? Less mobility. You're saying less mobility means less conductivity?
No, that means electron can't move. And they're so concentrated, so that's why they can flow. Like they have less space.
They're not listening to you. Okay, they have less space. Say it again. Say it louder.
I mean, they have less space to move through.
They have less space to move through. So which will increase conductivity?
No, it will not increase.
It will not. So you're saying it the opposite. If you keep on increasing the doping, the conductivity will not increase proportionally.
After a certain point, it may get decreased.
After a certain time, it may get decreased. Okay. It's one opinion here. So if you keep on doping, after some time, the conductivity will go down. Does it make sense? Does it make sense? Why?
Not really.
Not really. It should keep on going up, right? So if you keep on providing dopants, it should keep on going up, right? But I have not used the word mobility yet. We have been doing conductivity yet.
Maybe it will saturate at a point, but
They'll saturate at a point.
May
What will
increase.
saturate at a point?
the conductivity.
The conductivity will saturate at a point. So he's saying that it should become flat after a certain doping concentration. He said it should go down. But
Probably won't fall down.
it probably would fall down. Okay. Anybody else? The basic difference between a conductor and semiconductor is, in conductor we have free charge carriers, which we can move as we wish. But in case of semiconductor, we are incorporating them from outside. Right? So what matters for semiconductor is not conductivity, it's the mobility, which is this guy. And mobility is how fast we can move them. But now think about it, they were not there inherently, we introduced them. So there's a lattice already there with a very well-defined crystalline structure, and now you are overcrowding that structure. Mobility goes down. As you cross certain limits, the collision reduces the mobility of the carrier force. This is what I was showing you. And they have higher mobility, but it falls down ultimately. It's a function of quality of crystal, defects, interface, doping density, stress, and temperature. In both cases, you cross certain numbers, start going down. It's your resistor, but resistors are different. In N-type and P-type, they would have, because their mobilities are different. Holes are fat. Simple way to remember, holes are fat, right? There was something contained in that, like in that hole, which was electron. So electron is smaller, the clothing is bigger. So holes has more mass, fat is lazy to move. So holes mobility at one same concentration is always less, right? And it falls down in same way, like electron, right? So in CMOS, if I have N-type substrate or make resistor heavily doped P-type, will do the job. Make sense? It's called degenerately doped. Above 10 is for 23, 10 is 20 or 10 is 22 is called degenerately doped semiconductor. We will not even talk about symbol, but we'll talk about fabrication only. That's it. Device physics side of it. I want to go. So mobility is the important factor in terms of semiconductor surfaces, right? Unless we introduce a metal to do our charge transfer, or use heavily doped polysilicon, which is not essentially a single crystalline structure and acts like a magnet. We have been doing everything in the bulk so far, but now let's think about removing some material. Why did I put this guy up there? How do we make these engraved letters
VH.
in a metal? We do what?
H.
Etch. Right? How would they have done this etching? They had some covering on top in which they wrote our lecture, and then they opened that part where it was our lecture. They used something which was selective between that covering and the metal beneath, right? So it reacted only with metal and removed it, and we got words written which are at certain depth on the surface, which we can read, right? Top tallies, tell you that soldier wear, they are not essentially etched, they are engraved, right? But there are name tags which are etched, especially those which are on the doors for the braille in there, right? With the elevators, they have these words written which are a plate which is plastic, and then there are areas which are like that. So these are all etching, all examples of etching. What do we want to do? Selective removal of material. So our recipe should be selective. It should remove only the material that you want to remove. We can use photoresist or other materials, what we call hard masks, as protective layers for the rest of the area. So once you look at photoresist, this will come again. Photoresist is used to transfer the pattern, or it's used as a mask. It's used as a mask to transfer the pattern, or it is used as protective layer during etch, especially BHF. Two types we can do, either with wet condition, we do with dry condition. Both cases, wet etch is where we use liquid chemicals to do the reaction, or dry etch is where we use gases. We use combinations of gases, recipes of gases to do our process. So in both cases, we generally call them recipes. So when you start your process, you have to know the recipe. You have to know the recipe for that particular equipment, if it's done on equipment, or you need to know the etch rate of recipe if you are doing it with the liquid. So you might be using a beaker to do your process. So in any case, it's a reaction between the reactants, which results into products, and there is two types of etch. One is what we call isotropic, what the other is called anisotropic. What is isotropic?
It is uniformly.
Uniformly, which doesn't have affinity to certain direction, or maybe affinity is not the right word, which doesn't have any directionality to it, right? So it etches in all directions, same way. So BHF is simple example. BHF, you have oxide layer, you dip it in, it's going to etch the whole. You won't see any specific selectivity between horizontal or vertical BHF. It's going to etch just the whole patch. It will become clear once you get maybe a couple of slides. So selectivity and anisotropy. This is something that we'll see now. Essentially, the idea is that, say in this example, we used a dry etch process, and after the end of the etch, we see that we got 100 micron depth, but on sides, the etch did go on the sides. But if it was something which would have gone like this, we would have called it isotropic etch. It should have affected all directions in the same way. Oh, hang on with me, we'll see what is isotropy or anisotropy. But how do we control etch? In wet etch, we can change the concentration. In dry etch also, we can change the concentration of the reactant gases, right? We can change the temperature of the process, because for any reaction to occur, we need temperature. We need energy to supply to that process. We can change the temperature. Once the reaction occurs, there are byproducts. There are not byproducts, there are products, right, which come out of the reaction. Think about it. What happens when an acid and a base react? What do we get once an acid and a base react? Salt and water, right? So, what happens if you let salt dry? You get crystal. So the idea is that those products need to be removed. If more acid and base don't come together and there is just salt and water, reaction will stop, right? So the product needs to be removed from the surface. In case of etch, what does that mean? It means that if we have this example. So if I have this photoresist here and I'm etching silicon dioxide with BHF. So once this layer reacts, turns into some product, this has to be removed. So BHF can keep on attacking more of silicon dioxide, right? So how do we achieve that? In case of BHF, what we do is we gently keep on shaking the wafer. So reaction happens and products are removed. That's what it means, removal of etched product. So more of the material etchant can come in contact with the etched material. Same is the case in dry etching. Once you have the product, you want to suck it out, you want to vacuum, pump it out, so more reactant can react and do whatever it's doing. So in dry etching now, we have selectivity, again, same concept, selectivity, but we create plasma in etch. In liquids, we just have those chemicals coming in contact. In case of dry etching, we create plasma. Now what is plasma? How do we define plasma? Ionization of gases. Ionization of gases. So ionized gases are what we call plasma. How do we ionize them? Applying field, right? Applying field. The applied field we provide, and to maintain plasma, what do we have to do? Keep on supplying the power, right? But so there's this container, and we have these gases pumped in. When we are concerned, we want those ions to be produced. We create a plasma, right? Supply power, and that does the etching for us. So what we get is with dry etching, we get very high aspect ratio. So HAR will come out again and again. HAR is high aspect ratio, where we have one dimension very high than the other. This is probably a repeat of the same slide. So we define something as degree of anisotropy. So anisotropy is, it's defined slightly differently for wet etch or dry etch, but the basic idea is the same, that we want to have preferential etching in one direction than the other. So to create high aspect ratio features, we want the etch to be vertically preferential than horizontally. So we can get a deep trench, right? 100 micron deep and 10 micron wide. If it was not anisotropic, we would have been left with a trench which is 100 micron deep and 100 micron wide. Make sense? So, or at least it would have a globe shape which would have depth. So it would have been a sphere with all the axes passing through the center would be the same. Right? So it would be same in depth, same in width. That is not something called high aspect ratio. High aspect ratio is where we have preferential etching. Right? So we make high aspect ratio features with dry etch. In case of wet etch, anisotropy has slightly different concepts. Anisotropy is the preferential etching along different planes. Crystalline structure. So we want to have maybe something that etches 100 much more faster than 111. So what we end up is, we have, we'll see, we have shapes like maybe inverted pyramid, we have slanted walls which have very exact angle with the x-axis. So that's what is called anisotropy or anisotropic etch for wet treatment. And there's this figure of merit, what we call degree of anisotropy, which is the horizontal depth divided by vertical depth. So if it's completely anisotropic, we should have 0 for these, and we get high aspect ratio feature. If it's isotropic, this is not the height, this is the etching, horizontal etching versus vertical etching. You would get something, for isotropic these would be the same, right? They would result into number 0. But as ideally what we want high to be very, very, hold on. So, yeah.
V is for vertical.
V is for vertical. Yeah, we want vertical to be really high, really big. So the number is closer to 0. Right? Any questions? So, said a couple of examples of etch. Probably we'll stop on this one. So this shows us anisotropic etch versus isotropic etch. So start with same starting etch window, but recipe in this case is going in all directions. What we end up is something which doesn't have high aspect ratio. But if we have a recipe which is anisotropic, we end up with features which are very straight walls. Right? So that's the difference between isotropic or anisotropic etch for dry etch. Wet etch has to do with the crystalline planes. This is dry etch. We'll look at the anisotropy of wet etch. Any questions? Let's stop here and okay, the quiz. How many ways to turn in your homework? Hard copy or blackboard? Right? Pardon?
Is there maybe a quiz?
That was the quiz. How many ways to turn in your homework?